Average rate of change versus instantaneous rate of change is a very common topic in calculus. And one of the rates of change that we often like to look at is velocity. So the average rate at which an object travels is found by dividing the distance that it travels by the time that it takes to travel that distance. And we call that rate the average velocity. So it's the amount of distance that you cover divided by the amount of time that it takes to cover it. Now, along with speed, right, or the rate at which you travel, velocity also tells us the direction in which we are moving. Now, speed versus velocity. Speed is actually just the magnitude or the absolute value of your velocity. So if your velocity was negative 50 miles per hour, which would mean you're traveling in a negative direction, the magnitude of that would be 50, and that would be the speed. So the way that we find average velocity is calculated by dividing the change in an object's position, right? So it's dividing the change in an object's position, and generally the position function is represented by s of t. It is sometimes also represented with x sub t. So these are two different ways that you will see the position function represented. And we divide that by the change in time. So you can see that here, right? So if it's on some interval from t sub 1 to t sub 2, right, from time 1 to time 2, you would take the position at time 2 minus the position at time 1 divided by the difference in that time. Now this value here, the change in the object's position, this is also called the displacement. And what it shows is how far away from where we originally started the object is. Okay. So the average velocity, note, the average velocity is calculated using the position function, right? So when we're talking about average velocity, but the function that we're using is actually the position function. If we want to calculate the velocity at an exact specific moment, that would be an instantaneous velocity. And in that situation, we use the velocity function. And the velocity function is defined to be the derivative of the position function. So the main topic that we're discussing in this video is going to be rectilinear motion. And basically rectilinear motion is just motion in a straight line. So it's not like a parabola. It's basically moving straight up and down or straight left and right. And so it's following a straight line path. And its position can be defined by like polynomials or other equations, but it doesn't actually change like height or horizontal position. It's just moving either straight up and down or straight right and left. So generally speaking, when we talk about the velocity, we're talking about the instantaneous velocity. So the velocity of an object represented by v of t is defined to be the derivative of the position function. And then as we said before, the speed of an object is the magnitude of the velocity, or it's just the absolute value of the velocity. And then one other function that we often care about or consider when we're talking about position and velocity is also the acceleration function. So the acceleration function is actually the rate of change of the velocity. And so it's the derivative of the velocity, or it's the second derivative of the position function. Now, when we're looking at rectilinear motion problems, a particle is generally said to have a positive direction, right? So the direction is considered positive when the particle or object is moving upward along a vertical line, or when it moves to the right along a horizontal line. So if you're moving in a horizontal direction, moving to the right is positive, moving to the left is negative, as far as the velocity or the direction is concerned when you're dealing with velocity. And then moving up is positive and down would be negative. So that's an important thing to note when you're talking about the velocity. Okay, so let's go ahead and take a look at an example. So we said for time greater than 0, the position of a particle moving along the x-axis, so it's moving horizontally, is given by this function, x of t equals t cubed minus 12t squared plus 36t, where t is measured in seconds and x of t is measured in meters. So part A is asking us to figure out the velocity and acceleration of the particle at any time t. So since it's not asking us for a specific time, we're looking for the general equation for velocity and acceleration. Okay, so part A, First, let's go ahead and find the velocity function, which is just the derivative of, oh, in this case they use x. It's the derivative of the position function. So that's going to be 3t squared minus 24t and then plus 36. So that's our velocity function. And then the acceleration function is the derivative of the velocity function. So we can just jump straight into the second derivative of x here. So that's going to be 6t minus 24. So that would be my acceleration. So we could calculate the velocity and acceleration of our particle at any time t for this given position function. All right. B is asking us to describe the particle's motion for t greater than 0. So for the time after 0 seconds, what is the particle doing? So we know it's moving horizontally along the x-axis, but the key things that we want to know is like when does it stop, when does it change direction, and such. And to do that, we want to look at the velocity function. So we'll put a placeholder there for B, and we'll come back to it. So we want to look at the velocity function, and we want to know when the velocity is 0. And the reason why we want to know when the velocity is 0 is because when the velocity is 0, motion stops, right? It's no longer moving forward or backward. So it stops at that moment, and then it can either continue on or it can change direction, but that's what we want to know. So let's figure out where is the velocity 0. So we want to know where is v of t equal to 0, and that happens when this function here is 0, so 3t squared minus 24t plus 36 is equal to 0. All of these are divisible by 3, so I'm going to divide everything by 3. And then probably going to end up having to factor this. Okay, so I can factor to get t minus 2 and t minus 6 equals 0. So at a time of 2 seconds and 6 seconds, my velocity is 0. So at these times, the particle is at rest. So it is not moving at those times. So what's happening on either side of those intervals? So let's just do a quick sign analysis of the velocity function here. So if we take a look, here's, we'll just test some values here. Okay, so from 0 to 2, what is happening? So pick a number and plug it in and test whether it's positive or negative. So for time equaling 1, if I plug into this here, 1 minus 2, that's going to be a negative. That's going to be a negative. So a negative times a negative is a positive number. Picking a number between 2 and 6, let's say 3, that's going to be positive. That will be negative. So that means that that interval is negative. For greater than 6, let's say 7. So that's positive. That's positive. So that means on this interval, it's positive. So what does this tell me? So we know that the particle is at rest at 2 and 6 seconds. This positive value, remember it said when it's said to have a positive direction when it's moving upward or right. So in this case, since we're moving along the x-axis, we're moving right at the interval from 0 to 2, and then for t greater than 6. So it moves to the right on the interval from 0 to 2. Here, let's write it this way. T between 0 and 2, and also for t greater than 6. And it moves left for t in between 2 and 6 seconds. Okay. So that's the particle's motion. All right. I'm going to run out of room here. So I'm going to do a little bit of erasing. I'm going to erase, actually, let's move this. So part C. So the total distance traveled. So basically what's happening to our function, or to our particle? So we know it's moving right for the first 2 seconds, then it's moving left, and then it's moving right. So it's doing something like this. So it's going right, turning around, and then it's doing something like this. And now their exact position I'm not quite sure about, but it's doing something like this. So it goes right, then it goes left, and then it goes right. So if I just looked at the displacement, like if I just wanted to know here, let's say this was 8 seconds, the distance between time being 0 and time being 8 is not going to actually account for all of the distance that it traveled during those 8 seconds, because the displacement's only going to tell me how far away from where we originally started it is. So it's just going to basically tell me that length there. So the total distance, to find the total distance, I need to break up my particle's travel at each of its turns. So I need to look at the displacement between, or the distance between the starting point and where it turned, and then where it turned, and then between the this turn and the ending point. So what we're going to do is we're going to calculate, and also, since it's in this direction here, so for this portion on this part right here, that is a negative direction, right? So that means that my my value is going to be negative. So it's basically like canceling out whatever amount that we moved to the right. It's going to be canceling out. So we want to take the absolute value of all of our distances. So to find the total distance, basically you cut it up by the places where your velocity is 0, and you go from your starting point to your ending point. So we're going to kind of look at the S of 0, S of 2, and then from S of 2 to S of 6, and then S of 6 to S of 8. And we are going to take those. So S of 2 minus S of 0. And again, we want to take the absolute value because we want the actual distance that was traveled. So if it was negative, we don't want it to cancel out with some of the other values. We're going to add that to S of 6 minus S of 2. And we're going to add that to S of 8 minus S of 6. Okay, so we want to know this total distance. We're going to add all this up. So actually, I'm going to use my calculator to help with this. So the first thing that I'm going to do is in y equals, I'm going to throw in the original position function, because notice we're using the position function here. So my position function, so I know that it's in terms of t, but we're just going to use x's. So x cubed minus 12x squared plus 36x. So I don't actually need to graph it. I want to use what's stored here in y1 to help me do some calculations. So I'm going to go alpha trace, and it's going to bring up y1. And I'm going to evaluate y1 at 2. And then minus, again, alpha trace, evaluating y1 at 0. What is that there? So that's 32. So this is absolute value of 32 plus, and I'm going to just do second entry, bring up these same things, and then kind of put in my other numbers. So 6 and 2. So that's negative 32. So if we go in here, it's the absolute value of negative 32. So this is why we want to take the absolute value, because we don't want this canceling out with that there. And then the same idea. So let me show you the other way to get to your y1. So if you don't have the newer operating system, you have an older version of the TI 83 or 84, and you can't do the alpha trace, you can always get to the y1 by clicking on vars, tabbing over to y vars and choosing the function option and picking y1. So y1 of 8 minus y1 of 6 gives me 32 again, coincidentally. So absolute value of 32. So we're going to add all of those up. So 32 times 3, that is 96. So the total distance traveled is 96, and what's our unit? Meters. 96 meters in the first 8 seconds. Okay. So our second example is, again, looking at a position, velocity, acceleration. So it says a ball thrown straight upward. So now we're going to be moving up and down from Earth with an initial velocity of 88 feet per second is S of t, or S of t equals 88t minus 16t squared feet above the Earth, t seconds after it's been thrown. So this is our position function, how high the ball is off the Earth after t seconds. And then it says this equation is valid from the time the ball is thrown until it returns to Earth. So it goes up like this, and then it turns and comes back down. And obviously it's not valid before that, because you can't have negative height, and it's not valid after that because it will have hit the ground. So there are 5 things that we're looking for. We want to know the velocity and acceleration. How long does it take for it to reach its highest point? So that's like a maximum. What is the highest point? So that's the value of the maximum. When does it reach the ground? And then the velocity at the ground. So I'm going to focus on these 3 first. So what is the velocity and acceleration? So velocity is just the derivative, right? So v of t is the derivative of s. In this case, they're using s. So that's going to be 88 plus 16, or sorry, minus 16 times 2, that's 32t. So that's the velocity. And then the acceleration is just the derivative of the velocity, which the derivative of 88 is 0, and then the derivative of this is negative 32. So it actually has a constant acceleration, and it's actually constantly being pulled downward. It's decelerating constantly. And that is actually the gravity constant. Gravity is pulling it down at negative 32 feet per second squared. Okay. Part B is how many seconds does it take for the ball to reach its highest point? So this is indicating that we're looking for a maximum, which means we want to know when the derivative of the original function is 0, right? So we want to know when is the velocity 0. And if you think about that, that kind of makes sense, right? If you throw a ball in the air, it's going up, it's going up, it's going up. Once it reaches its maximum height, right? Once it reaches its maximum height, it's going to stop momentarily and then turn. And so when it's at its maximum height, the velocity is going to stop momentarily before it turns and falls back down to Earth. So we want to know when is v of t equal to 0. And that happens when 88 minus 32t is equal to 0. So 32t is equal to 88. Divide by 32, and what do we get? So 8 goes into both of these. 8 goes into that 11 times. It goes into that 4 times. So we get 11 over 4, which is 2.75. So after 2 3/4 seconds is when it reaches its maximum height. Part C is asking for the maximum height. So we basically just have to evaluate the position this time, right? Because we want to know what is its position at this time. So we evaluate S at 2.75. And this is going to be a calculator part again. So I'm going to go back into my calculator, go into y equals. I'm going to clear out this here, and let's throw in my new equation. So 88x minus 16x squared. Enter. And then let's again evaluate my function, y1, at 2.75. So this is going to be 121. So the maximum height is 121 feet, right? Yeah, feet. So that is the maximum height. Okay. Part D is asking how long does it take before the ball reaches the ground? So this is actually, again, using the position function. So in part D, when the ball is at the ground, when the ball is back on the ground, that means that S of t is going to be 0. So we want to figure out when the position is 0. So that tells me that 88t minus 16t squared is going to equal 0. So we'll probably factor this. So I can factor out an 8t, and I'm left with 11 minus 2t equaling 0. So this gives me that the ball has a position of 0 at time 0, and then also at 11 halves, or 5.5 seconds. And we know that it's going to be this second one because this one here is where we started, right? So this is the initial time. So it's going to be after 5.5 seconds. And the last part here, what is the velocity of the ball when it hits the ground? So we want to know what is v of 5.5. And so let's go ahead, whoops. What was the velocity function? It's 88 minus 32t. So let's go back here. So that's going to be 88 minus 32 times 5.5. And we can plug that into the calculator. So 88 minus 32 times 5.5. Hit enter, and we get negative 88. So this is telling me that the velocity was negative 88 feet per second squared. Now, this makes sense. It should be negative. It should be negative because on the way back down, when it hits the ground, it's falling back down. And remember, when the ball travels down, that's a negative direction. So it should be a negative velocity there. So I want to show you really quickly one other way that we could have gotten this number. And we can actually calculate the derivative of our function using the calculator. So if you go into second trace to calculate, you can calculate the derivative, dy dx. So we can calculate the derivative. Actually, I want to do this from the home screen. So actually I can go into math and choose the option 8 here, and derivative. So we're taking the derivative of x, and then, sorry, the derivative with respect to x of, and remember we have our function here in y1. So if we just go over here, we can input y1. So alpha trace, choose option y1. And the value that we want to evaluate at is 5.5. Hit enter, and boom, we get the same value. So you can actually calculate the derivative using your calculator that way.